The light is on right now, and the only thing powering it is a cup of backyard dirt. Not a metaphor. Not a demonstration using some lab-grade compound disguised as dirt. Actual soil pulled from 3 inches below the surface of a backyard in the middle of a completely ordinary afternoon. And it's running a small LED through a wire. That image alone should make you pause. Because if that's possible, if literal ground beneath your feet carries enough electrochemical energy to light something up, then every assumption you have about how electricity works and where it comes from deserves a second look. This isn't a party trick. It's a rediscovery. And the reason most people go their entire lives without knowing this works has less to do with the obscurity of the science and everything to do with what we've decided is worth teaching. Everything about modern battery technology is designed to make you believe electricity requires complexity. Walk into any hardware store and look at the battery aisle. Sealed units, proprietary chemistry, labels with warnings about disposal. The implicit message is that energy storage is a sophisticated industrial problem, one that requires factories, controlled environments, and rare materials. And to be fair, for high-performance applications, that's partly true. A lithium-ion cell in your phone is a precise, engineered object. But the basic principle underneath all of it, the movement of ions through a conductive medium between 2 dissimilar metals, that principle is ancient, and it doesn't require any of the complexity we've been sold. The modern battery industry represents roughly $140 billion in annual global revenue. That number matters because it explains the orientation of investment, research, and education. The industry has strong incentives to keep energy storage feeling like a technical domain, not through any coordinated suppression. It's simpler than that. When the profitable version of something is complex and consumable, the simple and permanent version just doesn't get airtime. There's no conspiracy here, just economics. And the result is that most people reach adulthood never having heard the term earth battery, never having been shown how the ground itself can serve as an electrolyte, and never having understood that the fundamental physics of electricity generation was figured out before the American Civil War. So let's fix that. Alessandro Volta didn't start with zinc and copper, he started with mud. Most people know Volta as the inventor of the first true battery, the Voltaic pile, around 1800. What the standard history lesson glosses over is how messy and grounded, literally, the experimental process was. Early galvanic experiments in the late 1700s used saltwater-soaked cloth, wet earth, and organic material as the medium between metal electrodes. The clean, controlled cells we associate with Volta came after years of working with whatever conductive material was available, and soil was frequently that material. But go back further. In 1836, a man named Daniel Vaughan documented what he called telluric currents, naturally occurring electrical flows moving through the earth itself, detectable with metal stakes and a sensitive galvanometer. He wasn't generating electricity. He was measuring electricity that was already there, running through the ground continuously. The earth is not electrically inert. It never has been. In the 1840s, researchers experimenting with early telegraph systems discovered something inconvenient and fascinating. Buried iron telegraph lines, when grounded at both ends, would occasionally carry usable current, not from any power source, but from the ground itself. William Walker, a British telegraph engineer, described receiving transmissions that appeared to run on earth current alone for periods when external power had failed. It was unreliable, yes, but it was real. The earth battery as a deliberate device was patented in the United States in 1874 by a man named Daniel Drawbaugh. His design was simple: 2 metal electrodes, zinc and copper, driven into moist soil at a distance from each other, connected by a wire. The voltage was small, but it was continuous, passive, and free. Drawbaugh used it to power a clock. A clock running indefinitely on nothing but ground moisture and 2 pieces of metal. That idea should have taken off. It didn't, because within 2 decades, the commercial electricity grid was expanding, and the incentive to develop low-voltage passive systems essentially vanished overnight. The technique didn't disappear entirely. It survived in military field manuals through both world wars as an emergency communication power source. The U.S. Army Signal Corps documented earth battery configurations as late as 1969 in field survival guides. It survived in amateur radio communities, where operators occasionally used grounded electrodes to power low-draw receivers. And it survived in the margins of off-grid homesteading literature, where people with no access to grid power looked for any passive source they could find. But it never came back to mainstream awareness. And there's a certain irony in that, because the underlying science hasn't changed at all. Soil isn't just crushed rock. It's a chemical ecosystem, and that distinction is everything. When most people think of dirt, they picture something inert, dry, passive. But biologically and chemically active soil is the opposite of inert. It contains dissolved mineral salts, calcium, magnesium, potassium, sodium, in concentrations that vary by location, depth, and moisture content. It contains organic acids from decomposing plant material, It contains microbial colonies that are themselves generating tiny electrochemical reactions constantly. Moist, mineral-rich soil is, in electrochemical terms, an electrolyte. Not a great one. Not as conductive as salt water or sulfuric acid, but functional. An electrolyte is simply a medium through which ions can move. When you place two different metals into an electrolyte, you create a galvanic cell. The two metals have different electrochemical potentials, different eagerness to lose or gain electrons. One metal, the anode, oxidizes, releasing electrons. The other metal, the cathode, accepts them. Electrons flow through the wire connecting the two, and that flow is electrical current. The electrolyte, in this case the soil between the electrodes, completes the circuit by allowing ions to migrate internally, balancing the charge. This is exactly what happens in every battery you've ever used. The chemistry differs. The medium differs. The voltage per cell differs dramatically, but the mechanism is identical. Your 9-volt alkaline battery is doing the same fundamental thing as metal stakes in dirt. The difference is engineering, not physics. Now here's why soil is limiting and why understanding the limitation matters. The conductivity of soil is determined by its moisture content and its dissolved mineral concentration. Dry, sandy soil has almost no ionic mobility. It makes a terrible electrolyte. Wet, clay-rich soil loaded with mineral salts conducts much better. The voltage from a single zinc copper earth cell in good soil typically falls between 0.3 and 0.8 volts. That's genuinely low. A standard AA alkaline cell puts out 1.5 volts. To get useful voltage from an earth battery, you need series connections. Multiple cells, each adding their voltage to the total. The current output, the amperage, is even more constrained. The internal resistance of soil is high compared to engineered electrolytes, which limits how much current the cell can supply before voltage drops. What this means practically is that a dirt battery isn't going to power your refrigerator. It isn't going to charge your phone at any useful rate, but it will reliably and repeatedly power ultra-low draw devices. LEDs running at 10 milliamps. Simple sensors, small speakers, clocks, which is exactly what Drawbaugh was using it for in 1874. You need 4 things, and I'd wager 3 of them are within arm's reach right now: zinc, copper, wire, and moist soil. That's the complete bill of materials for a functional dirt battery. For zinc, galvanized nails or bolts are ideal. Galvanized means zinc-coated, and that coating is your anode material. A 2-inch galvanized nail costs almost nothing. For copper, a short length of bare copper wire from any hardware store, or even a stripped section of standard electrical wire. For connecting wire, anything conductive works, and your electrolyte, as discussed, is already in the ground. Let's walk through a single-cell build. Take your galvanized nail and your copper wire, or a small piece of copper pipe. Push both into moist soil separated by about 6 to 8 inches. Don't let them touch each other. If the metals connect directly, you short the cell and get nothing. Connect a small LED across the 2 electrodes, with the positive leg of the LED going to the copper and the negative going to the zinc. If your soil has decent mineral content and moisture, you'll likely see the LED dim glow or flicker. In rich soil, it'll stay on continuously. To test your soil quality before committing, do this first. Take a small container, a plastic cup or a jar, and fill it with the soil you plan to use. Add enough water to make it genuinely wet, not just damp. Push your zinc and copper electrodes in, connect a cheap digital multimeter across them, and check the voltage. Anything above 0.3 volts suggests the soil has enough ionic activity for this to work. Readings above 0.5 volts, and you've got rich electrolyte material. Below 0.2 volts, try different soil or add a small pinch of table salt to the container. Sodium and chloride ions dramatically improve conductivity. That salt addition is worth discussing. Farmers and chemists have known for well over a century that adding electrolyte-rich material to soil changes its electrical properties. Salt is the simplest option. You can also use a small amount of wood ash dissolved in water, which contributes potassium and calcium, or compost-rich soil from a garden bed, which tends to have naturally higher mineral and organic acid content than subsoil. The electrochemistry doesn't care where the ions come from. It just needs them present. For a multi-cell series configuration, which is where this gets genuinely useful, you replicate the single cell as many times as needed, then connect them in a chain. The positive terminal of cell 1 connects to the negative terminal of cell 2, and so on. Each cell in series adds its voltage to the total. 4 cells, in reasonably good soil, averaging 0.5 volts each, gives you 2 volts, enough to drive certain LEDs brightly, power, a small transistor radio, or run a basic sensor circuit. The spacing between electrodes within a single cell matters less than keeping the 2 metals from touching. 6 inches apart is a reasonable starting point. Going further, 12 inches, 18, can sometimes increase output slightly because you're accessing a larger volume of electrolyte, but the gains plateau quickly. What matters more is the depth of insertion. Getting your electrodes 3 to 5 inches into consistently moist soil gives far more stable output than surface insertions that dry out when the weather changes. One practical note on electrode maintenance. Zinc anodes oxidize over time. That's the mechanism. That's them doing their job, which means they'll eventually be consumed and need replacing. In outdoor earth battery setups, a zinc electrode might last anywhere from several months to a couple of years, depending on soil chemistry and current draw. Copper cathodes are much more stable and rarely need replacement. Factor that into any long-term installation you're considering. Here's what the dirt battery actually powered. In my tests, and I'm not going to oversell this, across 6 separate cell configurations and 3 different soil types, standard garden bed, dense clay, and sandy loam, here's what consistently worked. A single red LED ran continuously and visibly in all 3 soil types, with the clay giving the best output. A small buzzer circuit activated intermittently in the garden bed, in clay soils, but failed in the dry sandy loam without salt addition. A 3-cell series connected to a radio receiver produced faint but audible output in the garden soil. An 8-cell configuration in the clay-rich soil, the best performer, measured 3.2 volts open circuit and successfully lit a small cluster of white LEDs at a visible brightness. Here's what didn't work: charging any kind of battery, even a small watch battery, within any reasonable time frame, powering anything with a microcontroller or display, running any motor, even a tiny hobby motor. The current ceiling simply isn't there for those applications with this kind of setup. The honest framing is this: an earth battery is not an alternative to your electrical grid. It's not an off-grid power solution for anything beyond the most minimal loads. What it is, genuinely and usefully, is a passive maintenance light, zero-input power source for ultra-low draw devices. A sensor that sends a signal once an hour, a remote indicator light, an emergency light source in a situation where no other power is available. For those applications, it's not just a curiosity, it's a legitimate tool. A single cell isn't impressive, but 6. Cells wired in series is a different conversation entirely. The practical scaling path for anyone who wants to push this further goes in one direction: series cells, optimize soil, and match loads. The load matching piece is critical. Ultra-low power electronics have proliferated in the last decade, driven largely by the Internet of Things sensor market. Microcontrollers that draw microamps in sleep mode. LEDs rated for 5 milliamp operation. Temperature and moisture sensors designed to run for years on a small coin cell. All of these become viable earth battery loads because their power requirements are so minimal that the current limitations of soil electrolyte cells stop mattering. A 12-cell earth battery array, properly configured, can realistically provide enough power to run a remote sensor node indefinitely. No solar panel, no wind, no maintenance. The ground does the work. That's not nothing. In agricultural monitoring, in remote environmental sensing, in emergency signaling applications, that's actually a meaningful capability. What this experiment actually proves isn't about dirt. It's about what you've been conditioned to believe is necessary. We've built an entire cultural story around energy that emphasizes complexity, infrastructure, and industrial scale production. That story is mostly accurate for the energy densities modern life demands. But it has a shadow side. It makes people genuinely believe that nothing simpler could work, that low-tech approaches to electrical generation are quaint history rather than viable technique. The dirt battery is a small but specific rebuttal to that framing. The physics hasn't changed since 1800. The materials are universal. The knowledge was real, and it still is. What you do with that is up to you. But the next time someone tells you something is too simple to work, remember that there's a light that ran on a cup of backyard dirt. And the only reason you'd never heard of it is that nobody had a financial reason to tell you. If this kind of first principles, back to basic science is something you want more of, the kind that cuts through the complexity and gets to what actually works, subscribe and you'll see it when I dig up the next one. And drop a comment with what you'd actually want to power with a setup like this. Some of the answers to that question have surprised me, and they might be worth exploring in a follow-up.